Okay, and then start with showing you an overview on low power systems and have a deeper look into the architecture of those. Therefore, I provided a short agenda with first the motivation of low power systems, why we do research work on those. Eric, you already mentioned good arguments and had a very good introduction to that, but I want to pick out some additional points. And then I move on to the chapter Low Power Platforms, where we have a technical deep dive into the architecture and to the implementation. And in the following chapter, then we see example and as a result of that, and we show what kind of applications could be addressed by those systems, although from our experience. And I will close the session with a short summary, and we get an outlook on what might come up in the future and what research questions we are addressing. So starting with the motivation, as you as already mentioned, there are a huge bandwidth of applications which can be addressed by low power systems, starting from industrial IoT applications, where I put the focus also on this slides, but also smart home applications, sport and health application, and logistics and tracking. And all these applications have in common that they need systems which are energy autarkic with the use of batteries, or even with energy harvesting techniques. And the requirements of those systems are less weight, less footprint and geometry boundary conditions. So saving energy is not only related to saving carbon CO2, but also it has an impact for the whole design of the system. And with longer lifetimes, you also can lower maintenance cost and you gain better EM performance. But of course, there are a lot of challenges to solve to reach the goal of low power systems. We have reduced resources, example given by reduced computing power and also memory, which might shrink the possibilities of software and algorithms which can be computed on their devices. We have always heterogeneous components and interfaces and peripherals because that systems interact with the environment. There are sensors which should measure the environmental conditions, and there are human interfaces and other actors like motors or other devices which have sometimes totally different requirements. And those challenges have to be addressed under the focus of low power design. Also, we have increasing complex system functionality, especially also in the wireless communication. We need higher bandwidth and higher sampling communication rates. So this is also a main factor for energy demand. And to show this increasing need for devices, these numbers already shown also by Eric show the growing market of IoT devices. So the demand for energy saving is immediate, and I will try to give you an overview in these slides how we can do this. Here, this slide shows the state of the art regarding already available platforms on the market. We see different performance levels. Here on the right-hand side, nearly embedded computing machines like well-known Raspberry Pi. And then on the left-hand side, embedded systems with minor resources, more for development, also with less energy demand. And we have had a deep look on most of these devices, and these devices are can be described as platforms for sensors, platforms for development, and also platforms for software development. But all these devices do not integrate power management with the focus of low energy demand and power saving technologies. And so our research question was how to address it with the same functionality as a commercial IoT platform. And this leads us to the IoT core towards zero power. So this is the basic idea for the architecture I will present you in the further slides to gain the functionality needed for attaching sensors, computing power, and also wireless communication, but with the focus on saving energy. So this low power platform in principle incorporates, of course, a main processing unit based on a microcontroller. Sometimes we also see benefits in using hybrid technologies with a microcontroller and an FPGA. There are different communication protocols and communication technologies available, and this will be more the focus of the following webinar on low power communication technologies, but has to be considered in a good and efficiency design. Sensors plays a major role in the whole platform architecture. They are attached typically to a wired interface, and here we see also a main factor to save energy in the configuration of the sensor in combination with the platform. All the other components such as memory, user interface, and actors are well known, and we will now concentrate on the energy supply and the interaction of the energy supply with the system, because this is the main possibility to control energy demand and to save energy. So this is the architecture, our proposal for an architecture relying on the one hand on a hardware design, which is of itself an ultra low power design, uses components which are saving energy due to their own design, but it's also reconfigurable and is a very modular approach. And this corresponds to a software development running on an operating system, on a microcontroller, which controls these hardware features, which controls these hardware functional blocks, and is connected to measurement functionality, which gives a feedback loop to that. In detail, this means we have, for example, switches which are able to switch off peripheral devices or unused functional blocks, but we also have level shifters to control the voltage domain of different interfaces, which means if I have a sensor device which communicates on a higher voltage level, then the power could be shifted on demand and in runtime to a higher or lower voltage level, and therefore we can configure the optimum level for the peripheral, and this also leads to energy savings. The measurement of the power demand from the system itself is done by an inline measurement. So the system knows which kind of component draws which kind of energy, and the software knows what kind of functionality is needed to achieve the quality of service level. Furthermore, we have an interface to the power supply, example given for an harvesting device or for a rechargeable battery, which can provide information on the state of charge or on the amount of energy which is available for the system. And with a multi-criterial optimization approach, we then can configure and control these kind of hardware in an optimum way to achieve functionality on the one hand and also energy savings on the other hand. The software development is done in an ecosystem consistent of simulation tools where we can simulate the needed energy demand based on several scenarios, typical scenarios, which are used in different measurement applications, such as in IoT applications for process control or process optimization for quality assurance of manufacturing process and so on. And then we can go to the hardware level and simulate each single step of measurement and communication and implement those software algorithms in the operating system. And afterwards, we are able to validate this approach due to our measurement equipment. And I can say that form a factor of 5 is possible to the state of the art. Here you can see the real device where the measurement was performed with. Using our in-house technology, it makes possible to also gain this form factor, which is very small, related to the energy savings and dimensions we can achieve with a smaller battery. Yeah, this is a photo on such a platform which integrates all these features the state-of-the-art platforms have by now. As I mentioned, there are interfaces to sensors, to other peripherals, such as interfaces also for communication, typical used in the industrial environment, for example, 100 megabit Ethernet interface or bus interfaces. And what we can also see is additional peripherals providing the energy due to batteries or energy harvesters. The validation of this architecture design, of this possible architecture design, is done by several measurements based on typical scenarios, as I said, and the simulated target, which was specified, was reached here in that special situation, and we can gain a factor of 5 of energy saving compared to the state-of-the-art platforms with this approach. Now I will come to some examples of applications. So the first one is a sensor we call it swarmy, because it's also not measuring for its own. It's connected with other devices, or could be connected with other devices. And this is specially designed for the industrial environment. So you can see that this device could be put into an iron-made manufacturing tool, or also integrated into machines. Here we can see a drilling machine to supervise the milling process or detect wear out of drills. And this device can last for a week from its battery, sampling 24/7 with a high sampling rate of at least 11 built-in sensors, and can be recharged by a wireless interface. This system relies on the architecture I already presented. Here you get some insights of the device. So we can measure, for example, light or accelerometer, magnetometer, humidity, and of course temperature. And these sensors are switched off if they are not needed. And of course, we have also those interfaces with an inline measurement support for the energy demand. Further examples can be envisioned. I will give you some details about these examples we have already experienced in. So also for environments, for harsh environments, for example, high voltage line, it's possible to put those devices on to monitor those lines, and sometimes they are not heavily loaded. So one can think that energy is not a problem at that point, but it is really, it is. So if the line is not loaded and only powered with voltage, then there are only a few milliwatts which are accessible for the device to get the power from, and with this it's enough to power the device with different measurement parameters and also with communication by, for example, Wi-Fi technologies. Further on, we also gained experience with these low power devices inside gearboxes, where the energy comes from a magnetic induction coil supplying the energy for this device, and it's enough and feasible to measure, for example, rotation speed, temperature of the different devices here inside the gearbox. And even is in the sewer down the earth, these devices are able to operate. Here you can see an energy harvesting electronic component which gains the energy from the temperature difference between air and the wall of the pipe. And this serves energy for the device, which is measuring electrical conductivity and pH value, and send them through wireless connection to the gateway. And even in agriculture, manufacturing processes, sometimes it's necessary to measure inside some substrate. So we have, for example, have here biomass, silage substrate, where the pressure and thickness of the substrate should be measured, and this could be done also even by those low power devices. And as you can imagine, battery maintenance and battery change here is not possible. So this device should at least last for 1 year, and with a battery capacity of 10 amp hours, it was possible to operate the device whole the year. Another example from Smart Health is a lab on skin approach, a miniaturized lab which is able to measure 30 up to 32 different channels of, for example, potassium. It could be charged wirelessly and last for at least 24 hours for sampling. Sampling and analyzing the sweat from the sportsman to give some optimization on training, for example. The communication is done by Bluetooth V5.2, and even with that, we have a very low power demand. Now I come to the end of my presentation. What I would like to show is an IoT platform which is could be extended by a very modular basis, and which is very energy efficient due to some optimizations in hardware and in software. And we have an innovative approach due to the runtime control of different elements in the hardware caused by software and feedback loops. And at least we have an ultra low power consumption of 1.44 microwatts in idle mode. This means that we can save in factor of 5 compared to the actual state of the art. Further applications in agriculture systems, for example, or process automation controls are possible, and also even in mobility application and smart home devices. And the connectivity is always ensured by different wireless or also wired data interfaces. Because of the importance of that topic of energy saving and efficiency, together with 40 other European partners, we are a partner of a EU project with a focus on the following topics, that we try to optimize energy harvesting devices fitting to that systems, low power wireless sensor architectures, as I showed today, and also optimize software implementation based on AI algorithms and AI techniques. I want to invite you to the following webinars, to my colleague Samuel Magasachi, who will show you the low power radio communications and what the research work is there, and also to my colleague Dr. Robert Hahn for revolutionizing low power devices with micro batteries. So I hope you enjoyed the presentation, and thank you very much for your attention. I'm happy to answer your questions. Thank you very much.